Welcome to Maths with EJD. Still on partial differential equations. Here we talk about quantum mechanics and the Schrödinger equation and how they are connected to partial differential equations. Are you ready for this? Let's go. So, as an overview, let's see the foundation. Of course, first of all, quantum mechanics describes the behavior of particles at microscopic scales where classical physics fails. Okay, so the Schrödinger equation, the Schro together, right? The Schrödinger equation, a cornerstone of quantum mechanics, is a partial, is a PDE, is a partial differential equation that governs the evolution of quantum systems wave function psi, which encodes the probability distribution of a particle's properties, like position or momentum. From a PDE perspective, from a partial differential equation perspective, the Schrödinger equation resembles a diffusion or wave equation, but is distinct, due to its complex valued nature, and probabilistic interpretation. Okay, so it comes in two forms. It comes in two forms. Number one, you have the time-dependent Schrödinger equation. So this is IH bar partial psi of r comma t all over pi t equals minus h bar squared all over 2m grad squared psi of r comma t plus V of R, comma T, psi of R, comma T. So that is the time-dependent Schrödinger equation. So here, psi of R, comma T is a wave function. As a wave function, and H bar is the reduced Planck constant. M is the particle's mass. Grad squared is the Laplacian. Then V of R, comma T is the potential energy. Potential energy. Okay. The term I H bar partial psi partial T drives the time evolution, while H bar squared minus H bar squared over 2m grad squared psi plus V psi, that's the Hamiltonian. The Hamiltonian, this is minus to be sure. The Hamiltonian determines the spatial dynamics. So it's time and space, the spatial dynamics. So that's the time-dependent Schrödinger equation. So the second one is the number 2. We have the time-independent Schrödinger equation. Okay. So, and that happens for stationary states. So that's for stationary states. So it means the system is in some kind of equilibrium. So here, minus H bar squared over 2m grad squared psi of R, no time, right? Plus V of R, psi of R, and that is equal to, oh, what did I do here? This is actually, yeah, okay, yeah, that's correct. That's fine. Yeah, that works. Okay. Equality, yes. So here, this is now equal to E psi of R. Okay, E psi of R. So this is an eigenvalue problem. This is an eigenvalue problem. It is an eigenvalue problem where E is the energy eigenvalue, and psi of R is the eigenfunction, which you can refer to as the stationary state. Stationary state. Okay, so the PDE nature highlights one, linearity. Linearity. So here superposition applies. Superposition applies, allowing wave function combinations. Then we have boundary conditions. Boundary conditions. Solutions depend on the domain and potential V. Then we have complex valued solutions. Complex valued solutions. So unlike classical PDEs, e.g., we've talked about all this a lot, heat equation, wave equation, and all that. Heat equation, unlike classical PDEs like heat equation, psi is complex. Psi is complex with the absolute value of psi all squared, giving probability density. Okay, that is Schrödinger equations as a partial differential equation. So let's try some examples and see what we get. So if we shift this here, and then let's use it alongside. It's been a long time for blue. So let's go blue now. Okay, so example one. Here we are interested in free particle in one dimension. So a free particle experiences no potential, meaning that V is equal to 0. So solve the time-dependent Schrödinger equation in one dimension. So we have IH bar d psi x comma t dt equals minus h bar squared over 2m psi square d squared psi x comma t dx squared. So to deal with this, step one, we have to assume a plane wave solution, assume a plane wave solution common for free particles. So that's like psi of x comma t equals ae raised by I into kx minus omega t. So that's a plane wave solution where, since you're talking about a wave, right, where a is amplitude, k is the wave number, And of course, is the omega is the angular frequency. Okay. So step 2. So we can compute derivatives. Compute derivatives. So first of all, we talk about the time derivative. Time derivative, which is partial psi, partial t. If you look at the partial psi, partial t of this thing, of this equation you assumed, of this solution you assumed now. So time derivative, so time is somewhere around here. So you're going to have some negative values. So a minus a omega into all that, I think. So we have minus, okay, with the I for sure. So minus I omega a e raised to power I into kx minus omega t. So, and the whole of this is just the same as I omega psi. I omega psi. This whole expression now is just where you're coming from. So that's I omega psi that way. And then we also have we have the spatial derivative of the same expression, spatial derivative. So for spatial derivative, right, we have partial squared psi, partial x squared. That is equal to ik all squared. If you differentiate twice, we have aei kx minus omega t. That is minus k squared psi. That goes. And in step 3 now, step 3, we substitute into the equation. So we substitute into the equation, which is we have IH bar now, will now be minus I omega psi, you know. So here we have the psi dt, and now we've got the psi dt to be this. So we substitute it into that original expression, and that will be equal to minus H bar squared over 2m. And whatever we get there, we have minus k squared psi into the original expression. So, and when we simplify, we have h bar omega psi h bar omega psi equals h bar squared k squared over 2m psi. So we can cancel, cancel psi, non-zero. I mean, if it's 0, that won't work. We can cancel it now. We can divide through by psi in short. So we have h bar omega equals h bar squared k squared over 2m. So in that case, we can still have one h bar goes. So we have omega. So this will cancel just one of this. So omega now is equal to h bar k squared over 2m. So we have this expression now for the angular frequency. So this, or let me continue with the same. So this relates frequency. This relates frequency to wave number. So the frequency is, angular frequency is omega, and the wave number I think is k. So this relates frequency to wave number, implying energy E is equal to h bar omega, which is h bar squared k squared over 2m, which is equal to small p squared, right? P squared all over 2m. where 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 P is equal to H bar K is actually the momentum. Momentum. So what's the interpretation of all this? Interpretation. The solution, psi of x comma t, which is equal to ae I raised power kx minus omega t, describes a particle with definite momentum P equals h bar k, but its position is delocalized. So that means it's uniform, meaning that the absolute value of psi bar squared equals the absolute value of a squared rather. The absolute value of psi squared is equal to the absolute value of a squared. So that's the interpretation of that example. Okay, so let's take another one. So blue comes here, and then I can have in place of blue this now. Okay, so example 2. So example 2. So let's talk about particle in a one-dimensional infinite square wall. That's example 2. So consider a particle of mass m confined in a box from x equals 0 to x equals a with v equals 0 inside and v equals infinity outside. Okay, now solve the time independent Schrödinger equation, minus h bar squared over 2m d squared psi f x over the x squared equals e psi of x, and 0 is less than x is less than a. So we have boundary conditions. Will be psi of 0 equals psi of a equals 0. So that means that wave function vanishes. Wave function vanishes at walls. So anywhere you have the wall, all the boundaries, the wave function does not exist. So let's go for step 1. So step 1, right? We can rewrite the equation. So if you rewrite the equation, we have d squared psi dx squared equals minus 2. So it's more, you are just moving everything beside this second order derivative to the right hand side. So you're multiplying by 2m, you're dividing by h bar squared, and you have a psi there already. So that's minus 2m e all over h bar squared psi. So if we define k squared to be 2me all over h bar squared. If you have that, right? So we now have d squared psi dx squared equals minus k squared psi. So this is a second order differential equation, which is pretty easy to solve. So that's minus k squared psi, k squared psi is not omega. Okay. So for this now, we know that in step 2, the general solution in this case is easy. So psi of x is simply a sine of kx because of the k, right? So a sine of kx plus b cos of the same kx. So this is the general solution of that second order ordinary differential equation. So in step 3, we apply boundary conditions. Apply boundary conditions. So here we say that at x equals 0, psi equals 0. Psi of 0 will be such that, at x equals 0, if you remember the boundary conditions, right? We had psi of 0 is equal to psi of a equals 0, meaning that at x equals 0 and at x equals a, psi is 0. So at x equals 0, it implies that psi of 0 is equal to a sine 0 plus b cos 0. So that simply implies that b, the whole thing here is equal to 0. That implies that because this is gone, so we have b times 1. So b is just equal to 0. So with that, say thus psi of x is equal to a sine kx. Okay, a sine kx, that's a new state because b is gone. All right, so we go for the next one. At x equals a, that's the other end of the wall. Psi of a now, so that means x is a. So psi of a will just tell us that a sine ka, a sine ka is equal to 0. So, and we know since a is not equal to 0, sine, we can divide through by a, that's what that means. So sine ka is equal to 0. So that means that ka is equal to arc sine of 0. We've done something close to this in previous cases. So that means that ka itself is n pi for n equals 1, 2, 3, and so on and so forth. So that now k is equal to n pi over a. Okay, so k is n pi over a. So in step 4 now, we can find energy. So here we know that k squared, remember we defined k squared previously to be this. So k squared is equal to 2me all over h bar squared. You remember that was how we defined it somewhere. Um, is it a long way off already? No, I think it's after here. I think we defined k squared. Yeah, this is the definition of k squared I was looking for. So we can bring it back here. So k squared is 2me equals 2me over h bar squared. And now we know k is n pi over a. So that will just be n pi over a squared. So with this, we can bring out the e. So this is what we are looking for now. We're looking for this e. So we can tidy things up there. So we have so if we just take this expression, so we can have E n equals h bar squared k squared h bar squared k squared all over 2m. So I mean that's are we talking about that yet? So for now, we are taking these two together. But now we are taking these two together for this next step. So we have En equals h bar squared k squared all over 2m. Okay. And it's also the same thing as when we take um these two together. Okay, let me write it this way. When we now take these two together again, so En will still be equal to h bar squared over 2m times n squared pi squared all over a squared, all still work together. So that means that En, so I mean we can just have it that way. I mean, this is the same thing as n squared pi squared h bar squared all over 2m a squared. That still works. So we go for step 5 now. Step 5, where we normalize psi. Normalize psi. I think that's a wave function. So that means that psi n of x will just be a sine n pi x over a. So then we require integral from 0 to a of psi n squared, absolute value of the omega n squared, I mean psi n squared, psi n all squared dx to be equal to 1. So that means that integral from a to 0 of a squared sine squared n pi x all over a dx is equal to a squared integral from 0 to a 1 minus cos 2 pi nx over a all over 2 dx. So the cosine term integrates to 0, over n periods. So that leaves us with a squared dot a over 2 equals a, which simply implies that a itself is square root of 2 all over a. Yeah, 2 times 1, 2 all over a. Then we'll take the square roots. Why? So a over 2. So the square root should cover everything actually, because if you look at this 2 over a, so I think it's better to have the square roots covering everything. All right, so thus psi n of x is equal to square root of 2 over a sine n pi x over a. That's the answer. What's the interpretation? So here, the energy is quantized, meaning that energy is directly proportional to square of n, and the wave function and the wave functions are standing waves. They're standing waves. So for n equals 1, psi 1 of x is square root of 2 over a sine pi x sine, it should be n pi x, right? But 1 is n now, so we have pi x over a at x equals a over 2, indicating the particle is most likely found in the center. Okay. There's a third example, but do I want to take this? Looks pretty long, or should I go for it? Okay, let's do it. So take this and this now. So example 3, still talking about quantum mechanics and Schrödinger equation. So this example 3 is about quantum harmonic oscillator. Quantum harmonic oscillator. So consider a particle in a harmonic potential V of x equals half m omega squared x squared. Okay, so solve the time independent, that is, the time independent. I mean, the time depend. I believe that the time independent one will be very complicated because it will be having to talk about two variables. To solve the time independent Schrödinger equation, minus h bar squared all over 2m d squared psi of x dx squared plus half m omega squared x squared psi of x equals e psi of x. So step 1, so the first thing is you want to simplify with dimensionless variables. So here, because of the dimensionless thing you want, you can define, I think I'd rather use eta because psi, I don't like psi. Let's do eta. Psi is a bit complicated to write sometimes. So you have eta to be equal to x. Now I don't know if the square root is covering everything. Okay. Okay, I guess it's not. So x square root of m omega all over h bar. So that psi epsilon is 2e all over h bar omega. H bar omega. So the equation becomes so we have defined these things to take over some of these expressions so that the equation now becomes d squared psi d squared psi d eta squared equals eta squared minus epsilon psi, this psi here. So we go for step 2 now. Step 2. So for large psi squared is way bigger than epsilon. So d squared psi d eta squared is approximately eta squared psi. So trial solution would be something like psi is approximately e raised to power minus eta squared all over 2. So if we substitute now, we have the psi, the eta equals minus eta e raised to power minus eta squared all over 2, and d squared psi, the eta squared is equal to eta squared minus 1 e raised to power minus eta squared all over 2. So this suggests that psi of eta is equal to h of eta e raised to power minus eta squared all over 2, where h of eta is a polynomial. Okay, so step 3. So in step 3, we substitute psi equals h of eta e raised to power minus eta squared all over 2, so that we now have the psi, the eta equals the h, the eta minus eta h e raised to power minus eta squared over 2 on one side. And then we have, let me bring this down, the squared psi, the eta squared, which is equal to d squared h, the eta squared minus 2 eta, the h, the eta, plus eta squared minus 1 h, all this multiplied by e raised to power minus eta squared over 2. Getting serious. So the equation becomes d squared h, the eta squared minus 2 eta, the h, the eta, plus eta minus 1 h equals 0. So this is the Hermite differential equation. It's a Hermite differential equation. Solutions are Hermite polynomials. Solutions are Hermite polynomials. Hn of eta when epsilon minus 1 is 2n for n equals 0, 1, 2, and so on and so forth. Thus, epsilon is 2n plus 1. E of n is h bar omega over 2 into 2n plus 1. So we go for step 4. Now we talk about the wave functions. So we have phi of n of x, phi n of x equals an hn into, that's an hn into square root of m omega over h bar x e raised to power minus m omega x squared all over 2h bar up there. I think I want to write that better. E raised to power minus m omega x squared all over 2h bar for n equals 0, h naught equals 1, such that phi naught of x is equal to a naught e raised to power minus m omega x squared all over 2h bar. So if we normalize, so we have integral from minus infinity to infinity of absolute value of a naught squared e raised to power minus m omega x squared all over h bar dx all over h bar dx is equal to 1, since we need it to be like some probability distribution. So we say let alpha be m omega all over h bar. So absolute value of a naught squared root pi all over alpha equals 1 implies that A naught is equal to alpha over pi raised by 1 over 4. Yep. Okay. Yeah, I think alpha over square root of pi. I think we need to check this properly. But from what we have is, so this is alpha over root pi. That's alpha raised by 1 over pi raised by half. We now square all of that. Or we take square root still. Yeah, we take square root. Okay. So what this simply means is that, yeah, from the look of things, right? Think this square root thing is, it means the square root is covering everything. Yeah, that's the only way this can make sense. Yeah, that's the only way that can make sense. Okay. So we have that, right? Thus, phi naught of x is equal to m omega over pi h bar raised by 1 over 4 e raised by minus m omega x squared all over 2h bar. And that's where it ends. And then we can talk about the interpretation. So interpretation, the ground state, we're talking about particle energy, all of that in quantum mechanics. The ground state, which is n equals 0, has energy E naught equals 1 over 2 h bar omega, reflecting 0 point energy, 0 point energy. The Gaussian wave function, the Gaussian wave function indicates the particle is localized near x equals 0 with higher end states showing more nodes. Before we see the Python code, let's look at some insights from here. So PDE insights, because we are relating quantum mechanics and PDE, talking about Schrödinger equations. So we have, first of all, free particles, free particle. So talking about free particle, the Schrödinger equation, behaves like a wave equation, with plane wave solutions, and continuous energy Okay, then we have the infinite well. So boundary conditions, quantize, okay, leading to discrete energy levels, typical of elliptic PDE eigenvalue problems. And then we talk about harmonic oscillator. So the potential confines the particle yielding polynomial solutions, or Hermite functions. Should that be Hermite functions resembling Sturm-Liouville problems, resembling Sturm-Liouville problems. I think I've done something about Sturm-Liouville problems under numerical analysis. So you want to check that playlist out, you know. Then, of course, in the end, right, the Schrödinger equations, PDE nature, PDE nature bridges classical wave phenomena and quantum probability with solutions dictated by the potential and boundary conditions. Okay, so this brings us to, oh yeah, thankfully, I need to show the Python code. Let's see what the Python code looks like. So I have something on quantum mechanics and Schrödinger equation talking about the Python code. So you see, we define the h bar. I think it's a standard value, which is the reduced Planck's constant in joule second, and we have the mass of electron in kilogram. That's 9.10 times 10 raised to minus 31 kg. You know, we're talking about very tiny stuff. Then length of the box is like 1 micrometer. I think 10 raised to minus 9, or is it nano now? Then n is, we're talking about number of grid points. There are 10,000, 1,000. Then dx, change in the grid spacing is L, that's length of box, divided by n plus 1. And then we have interior points from dx to L minus dx as defined in line 12. Then we have the kinetic energy coefficient is defined as minus h bar squared over 2m dx squared. And all that. So you can see this on Facebook as you check later. Sadly, I'm not able to put it on YouTube because of some restrictions. Right, so I just run this and it brings out a beautiful set of stuff at different energy levels. So you have energy level 1, that's the one in blue, I think. Yeah, that's the one for energy level 1. Energy level 2 is what you have in orange. So you see it's like the waves are forming better as the energy levels move higher. So this is energy level 1. Energy level 2 is this orange one. Energy level 3 is green. So it's more like you have some more patterns forming, not more wave patterns forming. And red is 1, 2, 3. So like you have, this one just has one trough, and the orange has one crest and one trough. And then you go for the third energy level, which is green. You have two troughs and one crest. And then energy level 4, red. So you have two troughs, I mean two crests, that's two maximum points, and two minimum points, that's two crests and two troughs. And you go to energy level 5, which is purple. So you have three crests and two troughs, like that. So that's how that goes. So you want to interact with the code and see how that works. So it's so beautiful, isn't it? So this is what we have in that situation. All right, so that brings us to the end of Schrödinger equation and quantum mechanics and Schrödinger equation as they relate with partial differential equations. So let me know in the comment section how helpful this video is for you. And let me know if there's a topic you'd like me to teach, a problem you'd like me to solve. And if you have not subscribed, be sure to subscribe so you don't miss out on any further thing. I have almost well over 700 videos on this channel for you to learn from. Be sure and hit the notification bell so you can always get alerted each time a new video is released. Then be sure to like and share also so that more people can have access to this great content I have going on here. So like, come your way again. Keep doing maths right. Bye.